Hello, this is Tracy, Math 135, Introduction to Statistics, and we are going to continue talking about Chapter 3, Topics and Probability. So here what we want to talk about is independent events. Two events are independent if the probability of one event occurring is the same whether or not we know anything about the other event occurring. Events A and B are independent if the probability of event B occurring is the same whether or not we know if event A occurs. So we want to decide if the following events are independent. So event A, a coin is tossed and the toss is heads. Event B, coin is tossed again and the second toss is also heads. Do these events, does knowing that you got heads the first time change your understanding, your probability of whether you get heads the second time? And the answer is no. These events are independent because if you think about coins, a coin doesn't have memory. It doesn't know what it got on its first roll. Every toss is independent. It doesn't matter how many times you get heads. Every time you toss that coin, the probability of heads is 50% and the probability of tails is 50%. That coin doesn't have a memory. Okay, next. Event A, a couple has a girl. Event B, a couple's second child is a girl. Does the probability of having a girl for the second child change if we know the first child was a girl? No, it doesn't. These two events are independent. Turns out that every child has an equal probability of being a boy or a girl. Period. Okay. Event A, a couple has a child with cystic fibrosis. A couple has a second child with cystic fibrosis. Does the probability of that second child having cystic fibrosis change depending on whether we know if the first child had cystic fibrosis? In this case, if you don't already know that you're carriers for cystic fibrosis, then the probability of having a child with cystic fibrosis is very small for just a random couple. Once you have a child with cystic fibrosis, we have more information. We know you're carriers. So that probability, before you had the child, the probability was small because you were just two random people. The probability you were both carriers was very small. Once you know you're both carriers, you have more information, and the probability that your second child has cystic fibrosis is much higher. These two events are dependent. Knowing your first child has cystic fibrosis changes the probability for the second child. Okay, number 4. Event A, a card is drawn from a fair deck and that card is a heart. Event B, you put that card back in the deck and you draw a heart the second time. Are those two events independent or dependent? Well, once you put that card back in the deck, you have reset. So those two events are independent. The second card, well, it's exactly the same as the first card. Same number of cards, same number of hearts, same probabilities. These are two independent events. Now, number 5, this is a different situation. Event A, a card is drawn from a fair deck and it's a heart. Event B, you don't put that card back. You keep it. And you draw a second card and it's a heart. Now, does the probability of event B change when you know that event A happened? Event A, you draw a card and you keep it. You don't put it back. Yeah, that changes your probability for drawing another heart. You didn't reset the deck. Fewer cards, fewer hearts. You have just changed things. Your probabilities change. So now what we want to talk about is that if we look at two different events, if they are independent, what's the probability that they both occur? Well, the notation for that is the probability of A and B. That's right here. P and then in the parentheses A and B. So the probability that A and B both occur if they are independent events is the probability of A times the probability of B. The probability that two independent events both occur is the product of the two separate probabilities. So here we've got some events and we want to calculate some probabilities. You have 13 pairs of socks. 3 white, 4 black, 2 red, 1 blue, 1 pink, 1 green, 1 yellow. You have 6 shirts. 1 white, 1 black, 1 red, 1 blue, 1 pink, 1 green. If you pick a pair of socks at random and a shirt at random, what's the probability they are both black? These two events are independent. Your socks and your shirts in separate drawers, you randomly pick one of each. It's not going to have anything to do with each other. So the probability that your socks are black, so the probability of black socks is, well, how many socks do we have? We said 13 pairs. And how many of them are black? 4 black. Now, what's the probability of a black shirt? How many shirts did we have? We had 6. And how many of them are black? 1. So what's the probability that you get black socks and a black shirt? It's going to be that 4/13 times that 1/6, which is going to give us a probability of 4 out of, well, what's 13 times 6? 78. And we do not need to reduce fractions when working with probabilities. A lot of times you'll wind up with, within the same problem, different probabilities have the same denominator. If you reduce, it's harder to compare. When you've got all the same denominators, it's easier to see what's going on when you leave your fractions in unreduced form. I know, we never do that, right? All right, number 2. You roll a fair 6-sided die 3 times. What's the probability you roll 3 4s? Each roll is independent. Dice don't have a memory. They don't remember what they got the last time. So the probability of that first 4, the probability that you get a 4, is 1 out of 6. Now for that second roll, what's the probability? Well, the probability you get a 4 is again 1/6. And on that third roll, what's the probability you get a 4? It's also 1 out of 6, because out of the 6 sides, only one of them is a 4. So the probability you get a 4 and a 4 and a 4 is 1 out of 216. 6 times 6 times 6 is 216. So what about the probability that you roll a 1, and then on your second roll you roll a 2, and then on your third roll you roll a 3? Again, these are independent events, so it's going to be the probability you roll a 1 out of 6, 6 possible rolls, only one of them's a 1, times the probability you roll a 2, which is again 1 out of 6, times the probability you roll a 3, which is also a 1 out of 6. So the probability of these 3 rolls is again 1 out of 216. Circle the answer so it's really easy to see what our answers are. All righty. Now what we're going to do is we're going to look at the probability that one event or another occurs. Not necessarily that they both occur, but that either one thing occurs or the other thing occurs or they both occur. So we're going to look at an experiment with 2 pieces to it. We're going to roll a 6-sided die and we're going to flip a coin. So we can look at this as an experiment with a single outcome with a sample space of, well, on your die, you could roll a 1, a 2, a 3, a 4, a 5, or a 6. And then on your coin, you can get a head or a tail. So you could roll a 1 in a head, a 2 in a head, 3 in heads, 4 in heads, 5 in heads, or 6 in heads. You could also roll 1 on the die, tails on the coin, 2 on the die, tails on the coin, 3 on the die, tails on the coin, 4 tails, 5 tails, 6 tails. So we have 12 possible outcomes if we look at it this way. Another way we could look at it is that we have our two separate sets of outcomes, a 1, a 2, a 3, a 4, a 5, a 6, and then the heads and the tails. What's the probability of rolling either a 5 on the die, either a 5 on the die, or heads on the coin? Either a 5 on the die or heads on the coin. Actually, let me change some colors here. So the probability, rolling a 5 on the die. Which outcomes here involve rolling a 5? Well, there's the 5 in the heads and the 5 in the tails. So you either roll a 5 on the die or we roll heads on the coin. So which of these involve rolling heads on the coin? Well, 1 on the die, heads, 2 on the die, heads, 3 on the die, heads, 4 heads, 5 heads, 6 heads. Alrighty. So we want to know the probability of either rolling that 5 or flipping heads on the coin. So out of these 12 possible outcomes, how many of them involve the 5 or the heads? Well, there's 1, 2, 3, 4, 5, 6, 7. So the probability of 5 or heads equals 7 out of those 12 equally likely possibilities. Now, another way we could do this is we could think of this as an addition problem. What's the probability you roll a 5? Well, the probability of rolling that 5 is going to be, how many ways do we have a 5? One way here and one way here. So that's going to be 2 out of 12 plus the probability that we get our heads. How many ways could we get heads? Well, we had 1, 2, 3, 4, 5, 6. 6 ways out of these 12 to get heads. But what crazy thing do you notice happening here? What is going on right here with this 5 and heads? This gets counted twice. Once as a 5 and once as a heads. So we need to subtract off that 5 and heads. We need to subtract off where that happens twice, minus 1/12. We put all that together, 2 plus 6 minus 1 over 12. That gives us 7/12. The answer we're supposed to get. So that leads us to what we call the addition rule. The addition rule in words. The probability that one or the other of two events occur is the sum of the probabilities of the two events minus any double counting. And we get that formula. Probability of event A or event B are both occurring. The notation, the probability of A or B equals the probability of A plus the probability of B minus the probability of A and B. If A and B are what we call mutually exclusive or disjoint events are events that have no outcomes in common. If we have mutually exclusive, otherwise known as disjoint events, then the probability that one or the other occurs is going to be just the sum of the two probabilities. If two events are mutually exclusive, then the probability that they both occur is 0. Mutually exclusive events have nothing in common. If one occurs, the other can't. So the probability they both occur is 0. So the probability that one or the other occurs is the probability of one plus the probability of the other. All right, we're going to put this into play with an example that kind of talks about a few things here. We're going to draw a card from a standard deck of cards. If we just plain pick a deck or pick a card from a deck of cards, what's the probability that we get an ace? Well, a standard deck of cards has 52 cards. How many of those 52 cards are aces? 4 aces in a standard deck of cards. Now, what's the probability that that card you drew, when you drew that one card, is a spade? Well, there are 52 cards in a standard deck of cards, and 13 of them are spades. What's the probability that that card you drew is both an ace and a spade? In other words, what is the probability that you get the ace of spades, an ace and a spade? Well, we know that. How many cards in the deck of 52 are the ace of spades? Well, there's just one. But we could have also gotten that by taking the probability of A, which is 4 out of 52, the probability of getting an ace, which is 4 out of 52, times the probability of getting a spade, which is 13 out of 52. If we actually do that multiplication, we find out that we get 52 out of 52 squared. And then we can cancel, leaving us with 1 out of 52. So the two different ways of calculating this give you the same result. The probability you get the ace of spades is 1 out of 52. That's the probability you get an ace and the probability that you get spades. Okay, so now what we want to look at is what's the probability that that card we drew is either an ace or a spade? What's the probability that it's one or the other? Well, the probability that we get an ace or a spade, how many of the cards are aces? Well, we've got 4 aces out of the 52. Oh, let me change my colors. Probability we got an ace is 4 out of 52. Plus the probability we got a spade, which is 13 out of 52. But what crazy thing are we doing? We are actually counting the ace of spades twice. So we need to subtract that off. The probability that we get an ace or a spade is the probability that we get an ace plus the probability that we get a spade minus the double counting minus the probability that we get the ace of spades. Probability of an ace and a spade. And when we do all that math, all that arithmetic, we wind up with the probability you draw either an ace or a spade is 16 out of 52. Alrighty. So here we've done some probabilities. We've talked about the multiplication rule and the addition rule, the probability that two events both occur, the probability that one or the other occurs. We'll talk a little bit more about this in the last video in this chapter coming up.